Hello, my name is Laurel Mahoney, and thank you for coming to the presentation today. Before we get started, I just want to give a little bit of background about myself. I currently work for the National Park Service with the Invasive Plant Management team, where we go around to the national capital area and treat and remove invasive species. Prior to that, I worked with Rock Creek Park in natural resource management, and before that, I worked as a development analyst with Aerospace Corporation. And with that, let's get started with the presentation. So today I will be presenting on utilizing Aqua and Terra Modis satellites to analyze degree days and their impact on the agriculture and energy industries in the Northeast United States. So this is actually a part of a NASA developed project that I completed with a group at the National Centers for Environmental Information back in 2017. I have retrofitted it a bit to focus mainly on agriculture and energy impacts. However, I will touch on the other part of the project as well, because I feel that it is relevant to the overall topic. And to give a little more context, NASA Develop is part of NASA's Applied Sciences program and addresses environmental and public policy issues through interdisciplinary research projects that apply NASA Earth observation satellites to community concerns around the globe. And I'll have more information on this at the end in case anyone's interested in applying, which I highly recommend. So to start off, I wanted to go over some facts about the climate, or climate in general, that deal with the overall problem that my group is trying to research. Also, please keep in mind that this project was completed in 2017, so there's a good chance that some of this information has changed, and sadly I didn't have time to update our numbers. So some of you may not know, but the year 2016 was recently determined to be the warmest year on record by both NASA and NOAA. Since 1977, every year has been in the top 10 warmest years on record when first ranked. And then specifically 2012 globally was significantly cooler than surrounding years such as 2010 or 2013, ranking as the 9th warmest year on record by NASA. However, regionally in the Northeast United States, 2012 was ranked the hottest year on record. These facts created concerns among the community globally and regionally, which helped to establish this project. These concerns include the need within climate monitoring agencies, such as NASA and NOAA, to better differentiate between relative warmth or coolness of individual years, seasons, months from the secular trend. The need for high-quality climate data at a higher spatial resolution that is of ample length, and the need to determine changes over time in climate data for practical usage in determining how to respond to possible impacts of temperature trends and variability within energy and agriculture sectors. Our project consisted of two parts. The study area for both parts of the project focused on the Northeast United States as defined by the National Climate Assessment. The first study period was from 1975 through 2016, and the second study period was from 2002 to 2017. And the degree days is what we'll be focusing on today. The project partners associated with this project are NOAA's Regional Climate Services Eastern Regional Director, Ellen McRae, and NOAA NCEI's Climate Monitoring Branch. Specifically, we worked with the meteorologist Karen Gleason. These project partners at the time only used in situ data to analyze temperature anomalies and calculate temperature reports. Our partners aim to improve and expand the current data extraction process by utilizing remote sensing data, NOAA datasets, and NASA satellites. The objectives for the development of this project were to provide a multitude of end users with an easily digestible perspective about temperature trends have changed to better prepare and plan for future temperatures. To utilize information from a variety of global temperature data and NASA satellite datasets, develop a temperature index specific to the Northeast United States with a higher spatial resolution than other indices currently being utilized, compute heating, cooling, and growing degree days using daily LST or land surface temperature data and in-situ temperature data, and finally, create a product for partners that has the potential to expand on a diverse set of end users to utilize the data. For the temperature score part of the project, the team utilized NASA GISTEMP to create the global temperature scores, and NOAA NCLIME grid to create the Northeast U.S. regional temperature scores. For the degree day part of the project, the team utilizes land surface temperatures, or LST, acquired from Terra and Aqua MODIS satellites. The Climate Reference Network also was used to supplement the LST data. For the degree days methodology, we extracted MODIS land surface temperatures from both Terra and Aqua satellites during 4 overpass times. Due to cloud coverage, there was missing data for some overpasses, which was why we filled in using an annual cycle model. After filling in the missing data, we employed an algorithm derived from our mentor, Anand and Amdar, which was used to obtain LST values. Next, monthly temperature averages from in-situ data acquired from the Climate Reference Network were used to calibrate the land surface temperatures, adjusting them to read as if measured 2 meters above the surface temperature. Finally, we created monthly maps of heating, cooling, and growing degree days using ArcMap. So a degree is defined by the measure a degree day is defined by the measure minus the base temperature or crop threshold. The degree days created using daily LST data show temperature thresholds in relation to both energy and agriculture sectors. Specifically for agriculture, Northeast crops, alfalfa, corn, and onion were used. To verify our maps, we compared them to the degree day maps created by the Northeast Regional Center, and they were synonymous with each other. So to give a little bit more clarity, because I know this can be confusing sometimes to people, heating degree days is when it's below the 65, so it requires heat in most households, while a cooling degree day is above 65 and would therefore require cooling in most households. Okay, so for example, if a day has a mean temperature of 72, there will be 7 cooling degree days because it is 7 degrees higher than the base of 65, and there will be 0 heating degree days. Depending on the base temperature, there can be more or less cooling and heating degree days. Corn has a growing threshold of 50 degrees Fahrenheit, so it can only grow when it is above 50 degrees. At a mean daily temperature of 72, so there will be roughly or about 22 growing degree days because 72 is 22 degrees higher than 50 degrees. These maps we created of heating degree days in the Northeast region for January 2003 and January 2017, highlighting the change in heating degree days in the Northeast in relation to the temperature trend throughout our study period. From these images, you can see that our methodology with LST satellite data provides high spatial resolution. So the big difference you can see here is that there is, one moment, there is now a majority of the state that requires less heating degree days than previously in 2003, now showing in 2017. And here, I hope it works, there's an animation of maps was created from the cooling degree days of the Northeast region from August 2002 to August 2017. This shows the change in temperature trend towards an increase in relation to the amount of days that require cooling. These maps of growing degree days of the Northeast region for onions, specifically for March and August of 2017. With onions having a threshold base temperature of 35 degrees Fahrenheit, you can see the difference of growing degree days between these 2 months, with March having fewer growing degree days than August. Once again, you can see from these images that our methodology with LST satellite data still provides high spatial resolution. Okay, so now for the impacts. For the agriculture sector, the big impacts after talking with our end users and with everything we provided has a better monitoring for growing seasons for specific crops at a higher spatial resolution, And with the hopefully growing historic growing degree days information, we'll show crop yield versus temperature trends, which allows for improved operational and potentially fiscal planning because they can look back on all the data through all their growing seasons. While with the energy sector, prepare for days with spikes in energy usage from heating and cooling degree day data, and provides energy sector information regarding power grid impacts, especially with any increases in the extremes that are occurring with more heating and more cooling. And for both the sectors, users were in need of the high quality degree day data set and a much higher spatial resolution for better interpretation and evaluation practices, which is what this deliverable will provide. One moment. And another thing I want to address at this part, we actually did get the chance with Ellen to converse with some of the end users and farms that were involved. And they were interested in the information and definitely wanted to use it, but they also requested a product that would provide the information in real-time daily data for them. However, given the scope of our work and the fact that you only have 10 weeks for an asset develop project, it couldn't be added to our work. And I wanted to add this point in because it just shows how our project could evolve in the future and showcase the information to better serve the end user. And sadly, since it's now 2020, we haven't been able to continue it, but we hope that NASA Develop and the NOAA groups will continue to work with them to keep going with this. So now for the second part of the project, this is dealing with temperature scores. The temperature score product allows users to differentiate the relative coolness or warmth of a particular year in regard to the warmth or coolness of surrounding years from the overall temperature rankings. The reason I chose to include the second part of this project is, and why I feel it's relevant, is because having the metric of showing temperature variation and overall trend just proves how necessary and relevant degree days are to these industries, especially with the amount of extreme variation that will be prevalent as I continue with temperature scores. So, for temperature score methodology, we first acquired monthly data from NASA GISTEMP and NOAA NCLIME grid. Next, we removed the long-term trend, 1880 to 1974, from the time series to just have the 1975 to 2016 as our overall time period. Then we used two different types of statistical analysis for the two different time periods, 1880 to 2016 and 1975 to 2016. Next, we divided the residuals by the group standard deviation to arrive at values analogous to z-scores. Okay, so I'm not going to go into too much detail with temperature scores just because this second part of the project wasn't the priority, but I am happy to answer any questions that anyone has or email out our paper to anyone that wanted more information about the technical process. So these are some of the results of our temperature scores for the globe as well as the Northeast United States. The first graph shows a color gradient of the global temperature scores, with 1 being colder in blue and 10 being a hotter year in red. From this, we can see that there is an upward temperature trend. The second graph shows the temperature scores for the Northeast United States, the same methodology as the first graph. As seen from these graphs, the Northeast and global temperature scores are not trending in unison. And as I was talking about before with how this is relevant to degree days and growing degree days, just those extremes of the 10s and the 1s and how that would be so prevalent and the information would be very effective for energy sectors as well as agricultural sectors. So in conclusion to our project, recent Northeast temperature trends as characterized by the running ranks and temperature scores have exhibited a great degree of oscillation between two extreme readings rather than clustering near the median. Land surface temperature data from MODIS is capable of providing higher spatial resolution temperature information. End users will use temperature scores for context and future quarterly state of the climate reports. And finally, degree days will also be operationalized within agriculture and energy sectors, as we discussed before. And now I wanted to include our video, which is a necessary component of NASA Develop project, and it summarizes our work in a nice way.
Every single year since 1977 has been in the top 10 warmest years on record when first ranked, reflecting the upward progression of annual global temperatures. However, it is difficult to differentiate the relative warmth or coolness of individual years, seasons, and months from the overall trend. This issue is representative of the need for scientists to bridge the gap between providing fundamental scientific data toward providing industries such as energy and agriculture with actionable and accessible information.
As a cross-cutting team from NCEI, our objectives for this project were to 1. Provide an easily digestible perspective of how temperature trends have changed over the last few decades, 2. Utilize information from global temperature data and daily satellite datasets, and 3. Compute heating, cooling, and growing degree days in order to differentiate a year's overall hotness or coolness from the overall trend.
For data extraction, the team utilized monthly data from NASA GISTEMP and NOAA NClimateGrid to create temperature indices.
The temperature indices we created show annual global temperatures in real-time perspective relative to the current state of the climate.
Being able to see how a certain outcome during a month or a season relates to not just the long-term average, but where we see the climate going is valuable in helping us plan for the near future.
In climate monitoring, we not only look at regions, but we look at specific locations, which this could apply to, or we could look at it on a nationwide basis or even for the globe. So this is definitely a scalable index, and we're really excited to have this.
To compute degree days, the team acquired land surface temperatures from NASA Terra and Aqua satellites to derive daily max and min temperatures. Then the Climate Reference Network was used to calibrate the data.
The degree days created using daily data show temperature thresholds in relation to both the energy and agricultural sectors. Specifically for agriculture, northeast crops were used.
Knowing how many heating and cooling degree days you have is really important to the energy industry because they can anticipate, certainly if there are trends, they can anticipate demand for use of electricity and of gases.
So different crops respond to different flavors of this degree day approach, and where it can be important is not just in the maturity of the crop, which does track along with degree days based on the crop, but even some of the pests that we observe.
This project could be used to help industries better prepare future operations, which would allow for easier adaptations to changes within the climate.
I also wanted to include our future work ideas at the time of creating this project to show how we would have adapted and moved forward. If the project were to be continued, this is what the team had planned. So as for future work, temperature scores may be used for research in other parts of the scientific realm, such as El Nino, La Nina, and the North Atlantic Oscillation. Degree day future work would have included adding more variables to the algorithm, such as proximity to the coast or vegetation index, as well as expanding the application to other sectors. Both parts of the project may extend to other regions as well within the United States and not just the Northeast. Finally, these are all the people that were a big part of the project as well as my teammates, and I just have to include them in here because we are extremely grateful for everything they did for us. Finally, this is my contact information as this is a recording, and if anyone has any questions, feel free to reach out. And if anyone is interested in NASA Develop, which I highly recommend, this is the website. The application window for summer 2021 is January 18th through February 26th, and the term dates are on the screen. Also, just some fun things I wanted to include in, the Langley NASA Develop office is actually going to be doing a project on Fairfax water resources, which I thought was really cool this coming spring. And there's also a multitude of projects focusing on food security and agriculture, which is what we're learning about today. Specifically, the group I was with at NCEI in North Carolina is doing one for Illinois, standardizing soil moisture anomalies for agriculture drought monitoring in Illinois using NASA Earth observations. So if you're interested in this at all, I highly recommend, and thank you so much for listening and coming out today.